Hello everyone. Today we are doing electric circuits and we are taking the questions from the September 2014 from the Western Cape. Question 7. Candice and Andy Siwe conduct an investigation to determine the EMF and the internal resistance of an unknown battery by experiment using 3 resistors. They use the circuit below with the first one resistor in series, then 2 resistors in series, and then 3 resistors in series. They also connect a voltmeter and an ammeter in the circuit. Okay. And then when switch S was closed, they obtained the following results. Okay. 7.1. Sketch the circuit in your answer book. Show in your sketch where the learners connected the ammeter and the voltmeter. So the voltmeter is always connected across the ends of the battery. So the voltmeter will go right there so that it measures the potential difference across the battery. And then for the ammeter, so this is the positive terminal of the battery, so the negative is this way, so the total current should flow in that direction. So it's either we are going to place the ammeter before the resistors, or we are going to place the ammeter after the resistors. So it means that we can place our ammeter right there, or we can place our ammeter somewhere there. Any of those 2 points should work. 7.2. Calculate the value of E and R that they obtained in the investigation by using their results. So EMF should be equals to I multiplied by R plus the internal resistance. We'll just choose any pair of results, 2. So we just say 2 resistors, and then on the other end we'll use 3 resistors. So when we use 2 resistors, the EMF should be equals to, so we have V external, I multiplied by R gives you the V external, and you have the current, so you need the internal resistance with the EM and the EMF. So this should, V external is given as 9.6. The current is 2.0 multiplied by the internal resistance. So this becomes your equation 1. And then the EMF should be equals to V external, which is 10.2. The current is 1.5 multiplied by the internal resistance. So EMF should be equals to the EMF. So it means that equation 1 should be equals to equation 2. 9.6 plus 2.0 R should be equals to 10.2 plus 1.5 R. 10.2 minus 9.6, that is 0.6. 2.0 minus 1.5, that's a 0.5 R. So 0.6 divided by 0.5 should be equals to 1.2 ohms. And then you'll substitute R into 1. You can also substitute R into 2. You should get the same answer. So this is 9.6 plus 2.0 multiplied by 1.2. So I am getting 12 volts. Okay, let's also try another method to find the answer. Option 2. This was option 1. option 1. For option 2, so let's look at our data. Whenever we add resistors in series, R external increases. So whenever R external increases, it means that your current should decrease. So we are saying that when we add resistors in series, R external increases, and then the current decreases, which is exactly what's happening there. So when we add resistors, the effective resistance increases. So what happens to the current? The current decreases. So it makes sense. If we were to plot a graph, the voltage will be on the y-axis, and then the current will be on the x-axis, and our graph will look something like this. So when the current is 0, the voltmeter will register the value of the EMF. Okay, so from this formula, EMF should be equals to V external plus I multiplied by R. We can see that the y-intercept must be what? It must be the EMF. And then on the y-axis, we must have V external. So V external should be equals to EMF minus IR should be equals to V external. So this is negative I multiplied by R plus the EMF. So that's what we are going to have. So this becomes Y is equals to MX plus C. We'll just fix this. R multiplied by I, because the current is what's on the x-axis. So this will become our I. The gradient should give you your internal resistance, and then your y-intercept should give you the value of the EMF. So we know that if we want to find the internal resistance, we should calculate the gradient of the graph. So resistance should be the change in V all over the change in I. So the change in voltage, we'll just use the values that we are given there. So we'll use 1 and 2. So the voltage is 9.6 for 2 resistors minus 7.8 for 1 resistor. And then when the voltage is 9.6, the current is 2 minus 3.5. 9.6 minus 7.8, 2.0 minus 3.5. So I'm getting negative 1.2 ohms. The negative is just because the gradient there is negative. So you can ignore the negative and just say 1.2 ohms, which is the same as what we got right there. So now we can say EMF should be equals to V external plus I times R. Let's choose the 3 resistors. V external should be 10.2, and the current is 1.5, and the internal resistance is 1.2. So we are getting 12.0 volts. Question 8. In the circuit represented below, the battery has an unknown internal resistance and an EMF of 12. When current flows through the circuit, the voltmeter across the battery reads 10 volts and the voltmeter across R2 reads 4 volts. Let's analyze the circuit. This is the positive, that's the negative. The total current will flow in this direction. We will still have the total current here. So the total current will flow through R1. When we get to this node, the current will be divided. And then we'll combine again, I total. So that's what's going to happen. 8.1. Explain what is meant by the EMF of the cell. So this is the maximum energy that a battery can supply per coulomb of charge. 8.2. Calculate the current through R1. Okay, so these two resistors are connected in parallel, so they will have the same voltage across them. So it should be clear that V external should be equals to the V that passes through R1 plus the V that passes through the parallel combination. Because if we combine the parallel combination, we will have a circuit that looks like this. So this is the ammeter, this is R1, and this will be R parallel. So for resistors connected in series, they have the same current but the potential dividers. So the voltage that passes through here plus the voltage that passes through there should be the same. Not the same, but when you add them up, they should give you V external. So V external is 10 volts. We are told that the voltmeter across the battery reads 10 volt. Okay. And then V through R1, we don't know what that is. And then V through the across like the ends of the parallel combination is 4. So V R1 should be equals to 6.0 volts. Now we can find the current. I should be equals to V over R. The voltage is 6.0 and the resistance is 2. So this is 3.0 amperes. So the total current of the circuit is 3. 8.3. Determine the internal resistance of the battery. Well, EMF is equals to I, because we do have the total, and then this is R multiplied by the internal resistance. The EMF is 12, and then IR gives you V external, so that's 10 plus I, which is the current, the internal resistance. 12 minus 10 divided by 3. So I'm getting 0.67 ohms. 8.4. Determine the resistance of R3. So for R2, we have the resistance as well as the voltage. So we can find current I1. So I1 should be equals to the voltage all over the resistance. The voltage is 4 and then the resistance is 2. So the current should be 2 amperes. But we know that I total should be equals to I1 plus I2 because the current is divided there. The total current is 3.0, I1 is 2.0 plus I2. Therefore, the current through R3 must be 1 amperes. Now we have the current as well as the voltage. So we can find the resistance. The voltage is 4 and the current is 1. Therefore, R3 should be equals to 4 ohms. Explain what would happen to the current and the resistance in the circuit if R3 was removed from the circuit and replaced with a wire of negligible resistance. Hence, what will happen to the reading on V1? Let's clean this up. Explain what would happen to the current and resistance in the circuit if R3 was removed. So we are removing R3 and then replaced with a wire of negligible resistance. We will connect a wire at X and Y. So that's our Y. Hence, what will happen to the reading on V1? Okay, so current always flows towards the path that has the least resistance. When we connect a wire, it means that the total current will flow in this direction. No current will come this way because we do have resistance. So we won't have any current coming this way. It means that R2 will be short-circuited. So the total current will flow in this direction. It means that the R external should decrease because remember, first we had R1 plus the R parallel combination. That was our R external. But now we no longer have the parallel combination because even R2 is what is removed anyway because no current will flow in that direction. So it's a short circuit. So R external should decrease because we are only left with R1. So R external decreases. When R external decreases, the current increases. And then from this equation, right here, the internal resistance and the EMF, they do not change. So when you increase the current, this causes the V lost to go up. And then this should go down because the EMF does not change. So V external should decrease. Therefore, the reading on V1 decreases.